You are not. Okay, good afternoon. Good afternoon to people present in person and good afternoon to online attendees. It's my pleasure to introduce our distinguished technical lecturer, Professor Alireza Haghighat, who is Professor and Director of the Virginia Tech Nuclear Engineering Program, Mechanical Engineering Department. He also is the Director of the Mechanical Engineering Program at the National Capital Region Campus in Arlington, Virginia. And before that, he was chair of the University of Florida Nuclear and Radiological Engineering Department and director of the University of Florida Training Institute. Prior to Florida, Professor Haghighat was faculty member at Pennsylvania State University for 15 years. And that was the time when I was there. And I have the privilege to work with Aaron Martin. Long nights, we used to have coffee at 2 p.m. The only open coffee shop in the state. So
They were waiting for us.
yeah, that were great times. And I learned a lot from Professor Haghighat. He's fellow of American Nuclear Society and he leads the Virginia Tech Fuel Transport Group. And over the past 35 years, Professor Haghighat has been involved in development of new particle transport methodology and large computer code for modeling simulation of nuclear systems. And there are names which are now legends. Titan, A3 and NCAP, which is the first actually hybrid, I would say, Monte Carlo code. And recently, which you'll be talking today, is virtual reality web application and interactive backup system for very fast Monte Carlo simulation. He has published over 280 papers and received several paper awards. And probably you're familiar that he has a book which is called Monte Carlo Methods for Particle Transport in two editions now. And he is recipient of 2011 Radiation Protection Shields Edition Professional Excellence Award and recognition award from the Office for Global Threat Protection for Leadership. He's active member of American Nuclear Society and he has been serving in different positions, including chair of the Active Division and Mathematics Computation Division and co-founder of Computational Medical Working Group. So in 2015, he contributed to the formation of Virginia Nuclear Energy Consortium, which is a non-profit organization, and now he's vice chair. He will refer to the great things that happened in Virginia with nuclear and with the consortium, and we're happy to see this development. Please join me, welcome Professor Haghighat to NSTEC.
Thank you very much, boss. It's always good to be among friends.
Yeah.
And I know, actually, I was telling somebody this Penn State, there was my office, which I think you took over, and you were next door to me. Someone trained in department heads. So if anybody wants to go to become department head, you should go to Penn State, get that office. You are ready to go. Anyway, it's a pleasure to be here. And I have normally, I think people who know me, I prepare lots of slides. And so I will try to go through all this quickly. And please stop me if there's a question or something you don't understand. Let's see, where do I stand? It's easier.
The camera is here, right?
Yeah. Oh, I have to be there?
Yeah, that's fine.
Okay. I don't want to block people. So anyway, so let me just mention a couple of words in the title, New Paradigm. Hopefully you will see what I thought it's something different than the standard real-time, high fidelity, and transport calculation. Generally, these words don't work together because the complications that the transport equation has and the number of unknowns that you are dealing with to get all that information fast. So I give you a background. I always give this couple of slides that somebody told me, I know these things. I said, no, it's okay. It doesn't hurt that everybody knows I talked about this new paradigm, which I call it MRT. I will explain what it is. Talk about rapid code. As you can see, it's a real-time analysis for particle transport and feature detection. And then talk about the validation and verification that we've been doing for the rapid code. And briefly, the last two, because we are moving forward with the use of the rapid code. So that's a set, that's an example I put there, and people say, I know, no, I think the key is this quantity we're trying to solve for is written in form of number density, which depends on the space, energy, direction, and time. No, most of the time, actually, we don't do time, we do a sleep state. But it's complicated to solve this quantity because of all the independent variables it has. So there are two approaches we use, what we call deterministic, which we use something called linear Boltzmann equation for neutral particle transfer. And it's approximate, diffusion, and all kinds of other techniques. And the other one is Monte Carlo, which is a statistical approach. And I always tell people the best way to define this Monte Carlo method, you literally can do an experiment on a computer with the use of random numbers and probability density. I put the equation, actually when you show this equation to students, undergrads especially, they get scared. It's not that difficult, actually. It's a balance of particle. The equation, the linear Boltzmann equation, is in a steady state form. Find, oops, which one is the laser? Okay, yeah. So it has a few terms in it. You have a flow term, you got collision term, which are actually loss term. On the right hand side, you got the switch. Again, the difficulty all is independent. We solve this equation to write the equation in different ways, what we call integral differential form and also integral form, and for different applications. Either one is difficult to solve. It's not, but the applications one. Monte Carlo, as I mentioned, is basically it's a simple example I have here. For example, if you have a shielding problem, you put a source, you send the particle to, you sample the different interactions, and you let it go through the shield, and because the statistical process, you have to average, you have to get a variance. Now, the Monte Carlo, I tell people is easy. And actually teaching the Monte Carlo is relatively easier than deterministic. However, the major thing about, since it's a statistical process, you need to have a small relative uncertainty. And to achieve a small relative uncertainty is very, very difficult, especially if you have a complicated problem. And so over years, people have developed these techniques called variance reduction techniques. And variance reduction techniques basically you choose the right particle for the objective you have somehow. And briefly I mentioned that. And also Monte Carlo, another thing about Monte Carlo is embarrassing in parallel, because these particles you can basically literally send individually, independently, and sample them. So it's relatively easy. However, for solving problems with high fidelity, it's very time consuming if you don't do anything special. So my group, we've done a lot of things throughout the years. From a standpoint, as Dr. Ivanov mentioned, trying to do parallel computing, vector computing, and also developing codes and different approaches. I have deterministic. What it means that different form of transfer equation, you put it together, so therefore you can use different regions, different equations. Monte Carlo deterministic, which was mentioned, is basically we are using deterministic to assist Monte Carlo. And there is something called importance function, which we use in order to accelerate the Monte Carlo simulation. The last one is deterministic Monte Carlo. It's something like my colleague or our colleague, Fazal Rahman from Georgia Tech, has put together a common code. And actually, rapid is somewhat similar, and we will see. So these techniques, obviously, people have been trying to use in order to make this calculation faster and easier. That's the purpose. So, if you know, a lot of times when I showed these things, I said I can solve this problem in seconds. They said, "Oh, who cares? I can have a computer. I could run overnight. I get it." So, okay. Now, this might be true for existing facilities, because existing facilities, we know it well, they are benchmark these things, they are verifying these things, so it's not important really, they don't need potentially anything, except if they want to do something unusual. But the challenge we have actually for existing reactors is planned life extension. We still don't know how these things are going to operate. Currently, I think majority of reactors in the United States has been extended to 60. So almost all of them actually the operating are extended to 60. And the 60 will be over, like in Virginia, or 60 will be over around 2030 something, correct? And then Virginia reactors, one of the plants, they got 80 years, they have 20 more years. It's not clear how these reactors are going to operate. And that's actually one of the major issues, in my opinion, that we need to have tools and capabilities to effectively simulate it. Now, the next one, which is obviously more important in some ways, is licensing, optimization, design of these new designs, which we have no idea how they are going to operate. We do not have prototypes, we do not have facilities to test certain things. So it really is important, as it says, we have to be able to do accurate and fast, and also high fidelity. And the reason all this, because we have to be able to literally simulate all situations that might be possible that this reactor design can tolerate or can be done. So, therefore, the traditional approach of using either deterministic code or Monte code, or even some of the hybrid, is not going to work, because in order to do detailed analysis, and then you'll be able to do all kinds of situations in reasonable time, you need a different way. And what is the difference? So we wrote a paper actually called Stanford multi-stage response function transport methodology. Multi-stage response function transport methodology. The idea here is if somebody gives you a problem, you do not just choose a code and start running. The first thing you got to do, you look at the physics of the problem and try to identify what can I do with this problem to simplify it, actually. So the idea here, as it says, if I can partition the problem into what I call stages or subproblems, whatever you want to call it, then if I can simulate effectively each stage with some form of response function. So basically I can calculate, idea is if I can represent that, I can calculate these response coefficients ahead of time, which is a major part of the calculation, calculating those coefficients. So if I can do that, which is says pre-calculation, where is it? Yeah. Pre-calculate these response function, response coefficient, adjoint function, whatever it is that you're representing your system, but you calculate it accurately with the best method you have, whatever it is. And in this case, say Monte Carlo is considered as most accurate technique we have. And then after you did that, then all you have a linear system equation. You got basically you put all these together and you solve a linear system equation. And this system you can solve literally in real time, depending on the example. So we have developed actually a number of other codes, but Rapid is the one developed for reactor application. So basically what we are doing, as you will see, I will show you some of the equations. Depending on the problem physics and objective, you write the linear Boltzmann equation in different forms, right? And you will see some of what I refer to. And literally, we've been solving all these problems: steady-state, kinetic, burnup, detector response, and each one has a different form of the equation. And then, if you wrote the equation, you pre-calculate all these coefficients, and actually there is a methodology, and we have a tool for calculating these coefficients. And then after you did that, and you calculate these coefficients as a function of different parameters. For example, in a reactor, you may have different age. you may have different burnup, you may have different temperatures. So you can calculate all these coefficients as a function of these parameters. So therefore, if you know them, you can simulate the reactor within the range of parameters you want, and combination of all these. And finally, you solve the linear system. So to credit the people who worked on this, the rapid code, actually, they are all graduate. And Bill Waters, Penn State, is professor there, Nathan Roscoff at Westinghouse, and Valerio Mascarina and his.
Got a quick question. How do you guarantee that the response functions are decoupling? Because I'm assuming the problems are coupled, but the response functions seem like they're decoupled and you basically cascade them.
Let me go through it, explain what we do it, and then if you have questions. Okay, so I will do some of the equations for different problems. For example, if you want to do eigenvalue of criticality or subcritical problem. So I wrote the equation. Basically, this is your general standard Boltzmann equation. If you're writing the operator form, correct? And that's the eigenvalue problem. You break up this F operator, which is a fission operator. You take the chi out, the fission spectrum, and you end up with this F hat and the chi, and then you multiply both sides. First, you do the inverse, right? And then you end up with, you multiply both sides with the F hat. What is F hat, by the way? Is only this segment, the fission zone, correct? I take the chi out, the energy dependence. And then you end up with the fission source on this side multiplied by a transfer function, which is coupling coefficients, multiplied by the fission source. So I have a linear system of equation, which basically is fission at one location coupled to the fission in other location as it is related, coupled together, correct? So if I produce fission here, it depends all the fission neutrons that are coming from all that. And if you discretize it, it's a simple equation. Again, if Fi is the region of interest that I'm trying to fission calculation, is a linear combination of all the fission that come fission neutrons that come from all the fissions, correct? And the key is obviously I have to calculate these AIJs, correct? The coupling coefficients. And then subcritical is similar. The only difference in subcritical system, not only you have fission, you also have independent source which initiate the subcritical modification. And so therefore you may have different spectra. So therefore you have different coefficients depending on the energy solution. And the question here, how do I calculate these coefficients? Basically, I put a source here, a neutron source, and let it go, please. And sample these AIJs and the vice versa. And this is basically the whole matrix can be calculated, right? That's clear. So detector response is much easier. If you remember, for detector response, normally if you have the flux calculated from the transfer equation, you multiply by detector cross section, you get the response. That's a standard approach everybody can do it. Now you can rewrite this using something called importance. And there's certain boundary conditions that you have to get this. Important, if you use importance function, basically importance function multiplied by the source gives you the response. The idea here, if I have a source distribution, if I have a detector, if I don't know the importance of neutron to this detector, if I calculate this, then I basically multiply by the source, I get the response. Right? There are two approaches, a standard and people have used it, it's nothing new, right? Now, the method we developed is something more like a second approach. So again, I wrote this detector response. Now, what we are doing here, if I have a detector I'm trying to calculate the response at, I start a source here at any point, say at any pin or at any pellet. And I say, what's the probability that this neutron is going to be transported through the system and interact at this detector, correct? And depending on detector, you have different response, correct? And that's it basically. All it is, so these coefficients have to be pre-calculated ahead of time for different detector, different locations, and different material and burnups and so on. And this gives you some idea about the process that we have. The first thing is all fixed source calculation. All these coefficients are fixed source calculation, and they are all independent. So you put the source, you get outcome. So you, in principle, if you have thousands of computers, you can run them all in parallel, and you get all your coefficient literally in seconds, depending on the amount of time one of them requires, right? Okay. Now, the other thing we do here, there are a few things. One is these coefficients are highly localized. I mean, a few rod here has no connection to the few rod down. It's really all localized. So the matrix is highly sparse, actually. So that, because if it was a full matrix, then it's forget it. You cannot really use it. And the other thing we are doing, as you will see some of the things I will show you, we are taking advantage of all the geometric similarity. And we are not blindly trying to calculate all coefficients. So we calculate for a segment if there's we translate it to other places. And this is all done through our pre-calculation algorithm that it doesn't for you. Just a representation of how these coefficients change as a function. So if I put the neutron source in the middle here, and I calculate the coefficients, it's going to drop by 2 orders of magnitude the next assembly, by 4 orders of magnitude the next assembly. So you can see how disconnected these plots. Now, this is a long list of things. I put it there, the slides are there. You can look at it. It talks about how we treat, we calculate these coefficients and how we effectively. Then we talk about 3D Bernoulli calculation. Now, 3D Bernoulli calculation is one of the important calculations you have to do, and there's a lot of issues with computation. So a standard approach is this. You start with number densities, you have your favorite multicolor code, you simulate it, you get some kind of flux distribution, you collapse it, you make it one group, then you use this in some kind of depletion code, you turn around and move and just go through this process. This process is very expensive because of the multicolor simulation. So what we have done literally, we replaced this by these coefficients. So we pre-calculate these coefficients as function of the specific power and exposure time, which combination of the two gives you the Bernoulli. And then you basically use rapid to calculate the fission density distribution. We update the information, we burn the fuel, and then you go back and forth by these coefficients. Basically, adjusting these coefficients as opposed to doing full multiple calculation, right? And I will show you some results that it's really impressive. This is more detail in case you want to look at the slide, gives you detail on how the inputs are created. The same thing. So the next thing is the control rod movements. In any reactor, you have control rods have to be moved. If the control rod moves, what happens? There's a local effect. So what does it mean? The coefficients are going to change, correct? Now, if you have multiple control rods moving, what are you going to do? Are we going to get all kinds of combination of all the control rods? The answer is no. You actually demonstrated that control rod movement is highly localized. So I can generate coefficients for a series of control rod movements for 1, 2, and 3, and then put it together. Correct? And that's very powerful. If we didn't have this, then we would have tough time actually because of. So it that basically shows you if we take all the control rods out, we get the coefficients, cases at different z level. Each control rod we bring it, we calculate coefficient, a set of coefficients, and then we get these deltas, and then we sum them all together for the control rod, which you already have drawn, and then get new coefficients, and then use it to get the coefficients. Again, it's very powerful actually from a standpoint of implementation, and we have used it for simulation of the typical reactor. This is the full flow chart of the code, and basically you have these stages. The first 3 really are pre-calculations, creating the database, and the last one is actually doing the calculations. So now I'm going to take you to some results again, please stop me if there are some questions and some clarification. We basically have done some few tasks, react codes, all the different problems. I only show you a few, and again, there are papers and go look at. So the first one is the some few task. This is actually a benchmark called GBC 32, which actually my former student, the current director of the lab, John Magnet, did this. Anyway, so anyway, John put this benchmark for task validation. So basically, this cache contains 32 assemblies. This is actually a standard cache, 32 assemblies. Typical Westinghouse PWR assembly, and the enrichment is about 4%. And so you will see the benchmark our calculation against MCP and several very often. So the first thing is preparing coefficients, correct? So I mentioned about symmetry. The PWR assemblies, at least part one, they have octal symmetry. So effectively, I have 39 pins. And then I consider 5 burn-ups, and the burn-up listed here, 5, 10, 20, 30, 40 gigawatt per metric ton. And I have one fresh. So about 234, exactly 234 calculation has to be done, right? And then each calculation we use is 45 minutes on 4 cores. And then total on 50C is about 12 hours. So my pre-calculation is done in 12, 13 hours, unlimited number. If you give me more cores, I can solve this much faster, right? But that's fine. And then coefficient, actually I will tell it every inch, actually, right? Okay, let's look at the example comparison of MCP, Monte Carlo code, and our code. So you have 32 assembly, 264 pin. Why is that? Because 25 are guide 2. There are 24 actual numbers when we do rapid calculation, and 200,000 numbers in calculation. So MCP, the eigenvalue, you see this is supercritical. The benchmark contains water. But that's the benchmark. It's not the real gas. It's not dry. It's a reactor actually. Anyway, so you can see that the difference basically 39 PCM. 39 should be much better transformer. Anything less than actually 50 is basically agreed. We calculate relative answer. So we calculate pin wise actually depend on the fission density. Pin wise actually depend on the fission density. Not many people can or do this, correct? Then MCMP we use for 16 core, we use for rapid 1 core, we don't really need. 9.5 days, 35 seconds. Okay, I spent 13 hours with limited number of cores to get my inputs, correct? I can do this 35 seconds and solve different problems. With MCMP, every different problem I have spent 9.5 days. Okay, if I want to analyze the system, good luck. You will do it. You 9.5 days every calculation is not good. So this actually shows you pin-wise. Again, it's difficult to see. These are pin-wise actually depend on filling density calculation. Then let's talk about reactive core calculation. This actually is work was done by Will Waters, right? For professor at Penn State. So he actually similar, there's a benchmark, is a full PWR, 241 assemblies, which is NEA OECD 240. He considered 100 axial level, so it's like 6.4 billion data point being calculated. There's a paper by the way in NSC if you are interested. So first eigenvalue. That's a serpent, that's ours, practically exactly the same, 5.3 PCM means nothing actually. Then computation time, serpent, 20 core, 1000 CPU. 1 core is about 12 minutes, correct? Pre-calculation, 700 CPU, 105 CPU hours for fission matrix coefficients. Again, unlimited number of cores. Again, if you give more cores, I can do it much faster. Now, this I didn't talk about. One of the things we do is assemblies, we translate. If you are on the boundary, we do boundary correction. That's why this TP is the boundary correction. Okay. Now let's take a look at detail of the Fisher density calculation. The first thing is just shows you the Fisher density between lines. This is relative difference practically between the serpent and rapid, practically the same. The yellow is almost zero. Then we took actually the I didn't fix this arrow, this star has to be here, the other one has to be on the other corner. So you took one pin, one of the pins at this location, 44, 44, correct? Compare prediction of rapid versus prediction of serpent. You see that, correct? The one that actually oscillating is serpent. The ones that is continuous is ours. You see that how nicely is a one pin inside this whole reactor we are comparing, correct? And this is actually show you average overall, you see exactly the same. Then you look at the uncertainty, serpent uncertainty movement square is about 2 hours smaller. The relative uncertainty of serpent is actually more than 10%. And remember, if people do some multi-color simulation, generally they say if it's more than 10%, it's not good. You better work a bit harder to get it below 10%. So why is that serpent? Well, part of the problem, like I have top and bottom few rods, you have higher uncertainty. You don't have part. That's why you have that. And as I said, those regions haven't been very changed. And sometimes, even 10% is underestimation because we use something called central limitium already. So therefore, these things are not exactly what you expect. So detector, what time I have actually?
Yeah, you can.
Okay.
Yes.
Because I want to get to the kinetic, which I believe that's more interesting than all these things. That's why. Let's see. So this is detector response calculation, which is basically you put the detector outside the cache, for example. This is just there's no problem. We show it outside. We put a helium detector just to test the process. So one thing about this problem, actually, we do two sets of. We use all our capabilities. The first thing we calculate the field of view, and you notice it's called Pentra. I use it to get the approximate angle to get the field of view of the detector because I don't want to calculate coefficients everywhere. There's no reason. The detector doesn't see too far. It sees the segment of the cloud. And then we use cadence methodology, what I mentioned before, in order when we do this transport calculation to get the response function, it has to go through this whole region. So you have to use variance. So that's what we are doing. So effectively, the tools we are building on the maps we are implementing in order to utilize our coefficients. Anyway, so quickly speaking, if you go off and calculate all these coefficients, which is you see a 2300 pre-calculation, 3.4 hours coefficient. These calculations were done every minutes. One of my students wanted to do as detailed. We don't need that, but anyways, they did it. It's fine. So the key is the field of view of this detector is only the one is these assemblies nearby. So the first row and the second row. And actually, if you look at the first two, almost 97% of the signal come from the first two, and the last three are 3%. Here you can see the example. So in the bottom is MCMP using cadence. If you don't use cadence, this is the calculated count rate that is detected. 16 for about 5 hours, correct? Then with rapid, two cases we are looking at. One is if I just consider the front two, and if I consider all of them, right? And you can see the difference actually is about 2%, which if I consider the back, the key is obviously what is this? That's not the same. That's right. And is in fact, so it's really there's no comparison. Let's call it that as simple as I can say. If I spend 4 hours to get those coefficients, And then I can reuse these things over and over, depending on what variables I consider in the calculation. So there, this is we made up a problem. Is actually made it more difficult because it was that benchmark problem. Standard PWM, we made it 5 by 5. Why I say it's more difficult because now we have significant drop of the flux potential actually is more difficult to simulate. But anyway, we did it. So we are simulating basically a reactor in 1 year with 10 time steps, and the time steps is 1 day, 4 days, and so on, so 365 days. And then we calculate that's the Bernard, the Bernard steps that we go. We calculate the K eigenvalue, and for rapid and also for second. You look at the relative difference, correct? The nice thing about these relative differences, they are going up. That's we want to see that because that's if it's going in some direction or the other, is some kind of bias. Notice these things out here. These are subcritical. I have larger difference. The reason partly is related to in the eigenvalue calculation on second, you really need to consider, I'm starting with this, but on those eigenvalue parameters, which change depending on the data, that you have to adjust those parameters. Anyway, in short, 22, actually these are not us, so these are 4, we don't call them 4.3 days, 21 minutes to do the same thing. So you burn the reactor in 21, which is really, again, there's no comparison. I can't really explain that the speed up is beyond the standard speed up we look at. Now, this is interesting. So we basically follow thousands of arguments, correct? And that's a better calculation generally used. Now, what you see here, I bring your attention. First, look at the nice colorful thing. What you see here is fission density. In the beginning of cycle, you see in the center, you have higher value, you have a higher value of the fission. And then as the cycle goes through, it drops. So what is happening? Basically, then take a look at the diagram on the left. Uranium-235, plutonium-239. What do you see? Uranium in the middle, it goes down, and plutonium in the middle goes up. That's exactly what you expect. You are looking at actually how you're burning the fuel. Beginning of cycle, you have a lot of uranium, so you have a higher value. As you deplete, it becomes flat. And I'm doing literally, you can follow literally burn up of the reactor as the reactor is operating. So let's move to what time I got. 20 minutes. Yeah. Okay. Let's see how fast I go on this. So one of the things, always you do computation, I was mentioning to someone, nobody believes me until I do experiment, right? You can write the best codes, the best thing you think you have. If you don't validate this on a real system, nobody cares actually, correct? Okay, so the question is, where do I validate it? Power reactor, nobody lets you close. Actually, we have a project we're trying, but then no one power reactor at this in US. Research reactor in the US also is difficult. So I went all the way to Slovenia. And my good colleague, Luca, who's the head of the reactor physics, and we've been talking about doing this. And his reactor is a well validated and well instrument. So I can actually follow like fission density distribution. Actually, we have these miniature fission density you can measure actually, or inside, which is very, very important actually if you want to do a high fidelity comparison. So the critical bench actually we has put a lot of things in the critical benchmark. So we validated this control rod movement. Actually, the VRS system that also we mentioned, we can actually test it. We can move the control rod. That's how the reaction is. Then the transient calculation also I will show you some validated the kinetic calculation, movement of control rod, insertion, control movement, the shift of the parts in time, in real time. Okay, this is their core. Is a typical, I don't know if it's a typical trigger is more square, it's circular, but this is a trigger reactor. And in principle, all these circuits can contain fuel. This is one of the cycles, they have full fuel in it. The uranium, the carbon hydride pin in the middle and uranium hydride as fuel for the pin, for controls. So in order to, now in research reactor, I always tell people research reactors are more difficult to model than power reactors. Why is that? There's no symmetry. There's no, and things can change. The burnouts can be different. Controls can be anywhere, correct? A research reactor has very nice homogeneity. They try to keep the power flat, correct? So I cannot use any symmetry. Okay? I have to model every bit of this fuel rod. So basically, our fuel, four fuel pins, and 3 of the control rods have fuel bottles. So when you pull out the control, fuel comes. So you have to model those. So if you consider 40 times 15, actually, we calculate efficient density, and also for control also the same, it actually do 16, you end up 640 positions that you have to calculate, and that's it. So take a look at results. First of all, these are efficient density calculation, rapid, and the serpent next to each other. Down here is the relative difference. The range of differences you see, plus minus 2%, and the uncertainty also for the serpent is pretty good, right? Now, benchmark is a benchmark problem. We provided this number, and the uncertainty of 560 relative uncertainty. Serpent calculation, our calculation, the relative difference serpent is 400 something, ours is 200 something. I wouldn't really go too far. They both are routine. I'm not going to say serpent is better or arbitrary. It's accidental. It's not. That's not important. Serpent 32 processor, whatever. I don't know how many days is that, and hours, 1 core 6 seconds. Right? There's no really, and I can move all these controllers left and right in 6 seconds, and get it. Okay, let's go. How much? Okay, so that actually 3D kinetic is very important. So and we don't really have real tools out there to use and listed what's going on at least in our community. So there is one group just been here, not in you, using diffusion code point kinetic. Okay, you get result fast. Good luck with accuracy. Okay, you get what you get. Then there are deterministic, that is either adiabatic or quasi-static. Steel is very, very expensive if you want to do this calculation. More recently, people have been looking at these hybrids, Monte Carlo, deterministic, and so on. So none of them is, okay, I should say that. Good luck. That's probably better. So let's look at the equations and see how we formatted for in terms of what's called transient difference. So this is the time-dependent transfer equation. So what you got a time derivative, and you got in transfer equation neutrons. You have 2 types of neutrons. We call it delayed and prompt. Delayed neutrons come from fission products. Okay, and that's all. By the way, they are very important because otherwise we couldn't control reactors. We wouldn't get reactors if the delayed neutron were. So, and then these delayed neutrons, they have, because in decay process, they have different half-lives. So they go from very seconds to 60 seconds or something like that. So we group them generally to 6 groups. So we can treat them properly when it comes to the differential equation. So now you want to do fusion matrix. Now, remember before I calculated one set of coefficients, which source is from. So now I got to do 4. Why is that? So ground neutron produce ground. Ground neutron produce delay. delayed neutron produce delayed neutron produce four set of characters. Not only that, these things have to be time dependent, right? Time dependent. Each trap will have an interval you have to calculate. So if you rewrite your transport equation, your prompt equation basically is a combination of prompt itself from delayed, and for the delayed neutron precursor equation, similarly, you got this decay, you have sources, but they're all in terms of fission. Nothing really special here. Now, it's actually interesting if you sum up and get the steady state formulation. We actually can separate delayed neutron from neutron, and you can report these things, which nobody has. So you calculate and do kinetic calculation, either way or together. You cannot generally separate them, except if you have some special idea. Not only that, actually, another byproduct of this formulation is calculating importance. You can transport the matrix and you literally directly get the importance function without doing any effort. The importance function is very important to estimate the kinetic parameters, which are basically kinetic parameters are property of reactor, and you use the importance function to average them to get effective values. And that shows here. I'm not going to go through it. That's the way we have calculated all these parameters. So the next thing is you have to effectively do time discretization. We use backward order. This is actually the area we can expand further, make it faster. So you can write the algorithm. So what I showed you is for fast transit. So you have to have these things calculated as a function of time. You can also write the equation for slow times, where the time constant is much larger than the life of neutrons. So the effective neutrons are generated and disappear instantly. If you do that, this is the equation. So it depends on these effective coefficients that you have to calculate. And you have to calculate the formulation I just showed. And again, discretize it. So these are three problems that we have tried at Trigger for related to the transient fission matrix. And I think I'm going to show you not the first one. Actually, flat top is not a Trigger. Is a standard experiment was done not a long time ago, I think, in Los Angeles somewhere. It's a very special experiment. There's a spherical ball in the middle, which is plutonium, and then surrounded by, and I'm not going to show it in case you are interested. It's there. The slides are there. I typed it. The other two I will discuss for you. So that's again that triple reactor I mentioned in the same core. In this case, we are going to calculate these coefficients, the effective lifetime of neutron, the beta effective, and something called alpha velocity, which is the parameter one can measure. So the first thing to show you, remember importance as I mentioned, importance of neutrons. So prompt importance and delayed neutron importance, and the ratio of delayed to prompt neutrons. So what you see here, prompt neutrons are fast or faster than delayed neutrons. You can see there's less things happening for prompt neutron in the middle than for delayed neutron, because the delayed neutron quickly interacts in the medium. And the ratio you can see again, delayed to prompt higher here and lower on the boundary, which basically fast neutron can go outside. These are the things actually have significant benefit of trying to identify and sometimes design reactors based on understanding of how the different type of neutrons are behaving. So look at these parameters I mentioned. Rapid calculations given here, certain calculation practically always. The calculation time 95 seconds to 8 hours 44 minutes 16 core everything we are using for certain. And the pre-calculation was done. Each calculation takes 290 seconds, but for the full all the efficient coefficients is about 7 hours, which is really not much. So let's talk about this problem. This problem actually utilizes all the techniques, most of the techniques we have used. So you see here, the transient vision matrix, the controller of movement, and all the detector response. So this is an experiment. Basically, we are bringing the control rods in. There's a shift in the flux. There are detectors outside that they follow this shift. This clear? So all these calculations are done together. You know, there's no, normally what you do, if you want to simulate this, first you do your core physics calculation. You get the vision density. Then you have another code to do your detector response calculation. If you do control rod movement, good luck, because that's another complication. So basically, that's the reactive core. Or control this color thing, other than yellow, or control rods. The one we are moving is this one that is called transient control rod. There are detectors on the top and the bottom. So these two represent detector up here. These two detector down here. One is on bottom, and so as the control rod is moving, you see here very nicely the power goes down, what they are detecting. Now take a look at something like happened here. So the control rod comes in and bounces back. And actually you are tracking, which is really nice to see. And that shows the detail that you're following this control rod. This is another one that is, again, not many people can look at these things. So we have all the detailed vision density distribution for all the delayed neutron and prompt neutron. In order to show it in one diagram, so we are integrating and trying to see how they behave as a function of time. So the top one is your prompt neutron behavior as the control. So immediately you see effects of the controller movement on the prompt neutron. The delayed neutron, you can see 1, 2, 3, 4, 5, 6, and take a look at the half-life. 51 seconds, 0.24 seconds. So you can see that the ones that have short half-life, they follow prompt neutron behavior, and the ones don't, they don't, basically. So you can see that these 1, 2, 3, 4, actually, or rather, 1, 2, 3, 4, they somewhat follow the behavior of prompt, but these two that have long half-life, they don't change because they are not affected by the. Again, this type of thing, good luck. I really don't know who has even looked at these things per se, let alone calculating. And this actually shows you is an animation of the same thing. So you have, you see this as a function of time goes through the process, and on the right you have prompt, on the left you have the one with short half-life, and the middle you have with the long half-life. This and this, the side one follow each other, and the one in the middle also doesn't follow because of that half-life. Okay, talk about computer time. So actually this is interesting. So actual computing time for this calculation is 24 minutes. And we look at what fraction of time is spent for the complex. Take a look at it. To read the database, to read the coefficients, we are spending 12 minutes, which actually the idea is to make this fast because database has become large. How you access to the large database can be time consuming. To do actual the parameter calculation 13 seconds, the time depends, the DRM is about 11 and 24. So obviously we can, and this is on one core. We are using one core to do this all 3D calculation. And then it shows you pre-calculation. Again, one calculation is 391 and 260 hours on 54 because these are time dependent. Or what is coefficients on calculated time dependent. Now, you notice I don't have any code comparison because no code can do this. I don't have, and I would sit there for months and days to get one calculation from some code. This is clear, but I validated it. I validated it based on, and that's why I'm using this research reality. Okay, next one. So one of the things about computer codes is important for the user to be able to use easy. Not that you have to spend hours and days to prepare an input, hours and days to prepare to get outputs. That's not good. You know, as an analyst, you don't want to waste your time. So this is how has been one of the things I've been 12 years I've been thinking and what to do. This is not good because it already inputs that people. So we developed this web application, which I can run it on my server. Is your interest. Yes. So basically what it does is all graphics literally. You change something, input is prepared, rapid is run, diagram comes in 3D diagram. And that's what's called VRS Rapid, and it has some virtual reality images that you can actually put your information inside. The other thing you see here is diagram. I'm standing on top of a spin view, okay? And this is actually this immersive environment. I don't know if you have it, possibly you should have it on campus here, which is basically a kind of cube you walk in. It's all images. These are all colors. And I have some kind of wand, and I can literally go inside. I can go up and down in this spec field. I can go inside the actual radiation, right? It's important if we have tools like this, not only for operators, for training, and for ourselves, if we are developing methods. If you can see exactly what's going on in the system. So the next thing is this again. I think some of the students might have participated in my workshops in the past. Anyway, so I showed this diagram. 1986, what happened? I graduated. Very good year. Not a very good year, actually. You all know what happened in 1986. No? Sure, no. Anyway, that was my very good time. Anyway. So I graduated, I joined Penn State at that time, and I started doing these things, you know, parallel vector and all kinds of things. You see here, we didn't have many computers, right? Mainframes. I would say if you want to do 3D, basically months, years, who knows. Then we start developing these codes. Mentioned Pentran, Atrium, Titan. Alias, I think, actually someone I talked to is electron transport. It's something similar to A3. But here also, it's not very good. Months or days or lots of computers, that's not my interest. So then it came up with MRT methodology, and basically literally you can do this calculation in minutes, seconds, literally on your finger on yourself. And I think this is really the way we need to do things. Let me say it as simple as I can. The last thing I will show you is a project we have with NRC, actually, the funding of NRC, to develop, as it said, a machine learning algorithm for monitoring reactive cores. And this is basically a combination of computation using rapid to calculate detector responses. And there are two things, reactors. One is a trigger reactor. We want to validate our tools on the trigger, and then we want to test it on the North Angle power plant with the Haghighat. We can put. Now, what is this, by the way? This is another anti-neutrino detection system. I work with a good group of colleagues from physics department. We've been optimizing this detector, and the idea here, if we are successful, the idea here to get rid of info detection. Combination of X-core neutron and anti-neutrino detection, we can do the same thing, and the computation is rapid, which you get into distribution. And then you can get rid of the info detector. If we can do that, existing power plant would benefit, and our future ones significantly. Long list of things we are doing, and validation, testing, and development. So I think with this, I thank you for listening to me.
So questions, comments, first from me person, and then Mario, can you see?
Yeah.
So when you did the delayed neutrons, it looked like you're doing you're assuming homogeneous generation across the core, that you were not taking into consideration the energy dependence of the yield of the light neutrons.
No, it's not homogeneous. It's detailed neurons stimulated to get the coefficients. There's no homogenization. What I showed you, I just want to collect all that information. I integrate that one. That's an integral over the space, so I can see, you can see the behavior. So I have detailed information everywhere. And it goes for delay neutron, all the groups and also problems.
So the isotopic varied across the reactor core axially.
Yeah, whatever it is. Yeah. So it's very powerful. I've been preaching to our community. Pay attention. I think we gotta move from the standard way of thinking. I tell people, you saw this equation over and over and over. The number of animals do not change, and actually increase, not that they change. So there's not much you can do with this equation. This is what it is. Monte Carlo is what you see. That's what it is. Basically, what we have done here, we pre-calculate things once. You do those calculations every time. You see what I'm saying? And actually, there are other benefits of this methodology. Everything is based on fixed source calculation. One of the issues with Monte Carlo is also eigenvalue. Monte Carlo has issues, which some people pay attention, some people don't. But that's another issue. That when you do fixed source calculation, you have none of these issues. So effectively, and that's another benefit of technology.
Yeah, just one question about, did you try to simulate accidents or interior damage?
No, not yet. We are looking at simulating pulse, maybe that's very fast. During an accident, obviously, for example, we did something minor. If you consider spent fuel pools. So spent fuel pools, one of the major issues they have is those racks which contains absorbers. And those things may degrade or something happens. So we actually generate the coefficients as functional density of the range of density of these absorbers. And then we simulate it. So that's, I was talking with my good friend, Dr. Wu, that with this tool, we actually can generate all kinds of variation of the system, and you can get the range of outcomes, which is basically gives you, okay, literally anything you do, this is all you get. So when it comes to licensing, you go to an RC, okay, this is what I have. I've tested everything in literally, because one of the issues with licensing and RC, anytime you give them numbers, a lot of times, oh no, I need experimental data. Well, we don't have a reactor, we don't have a facility. How do we provide experimental data, right? And that's a major issue, especially with next generation design, which we really don't know. We really have to have a very fast tool and accurate to be able to do all kinds of situations.
I'm just asking the question because what I understand about the response function methodology and joint, if you did not recalculate the situation, you will have to take it into account. Right?
Yes.
So this will add to the.
The point actually, I'm envisioning even having on-the-fly generation of coefficients. Because if I got thousands of computers sitting there, correct? I can generate these on the fly, literally. Situation changes, I generate it.
Only if you know the physics.
But if I don't know the physics,
The physics,
you
you say physics, but I say different.
just a moment, going back to my friend over there. If the accident happens before the system, correct? Then I have to basically make up all these different situations.
Yeah.
And based on these different situations, I create all these coefficients. And as far as I'm concerned, I got thousands of computers, there are hundreds of thousands of core in all these good national labs. I really need an hour of them. I don't need, and because these calculations are all done independently. You see, that's so important. They are naturally parallel, correct? I don't need thousands of years. I need literally, if you give me thousands of code, I can calculate all these things literally in the unit of one calculation. There is so much you can do, actually. This is, I've been telling people, I want to get involved in this because this methodology can do a lot of good. And I'm hoping actually for thermohydraulic people to do something like this, because if I'm going to do multi-physics, I want to get your results faster than hours and so on. So,
At the same range.
yeah.
Other questions?
Is the code open source?
No,
Yeah, question.
no, well, let me say it this way. In the United States, nuclear codes are complicated, correct? We cannot just simply give things to people, correct? Now, this code actually in some ways might be easier because I rely database, right? Database has to be calculated with another nuclear code. In some ways, it's different. But still, there is a lot of issues. You have to go to export control. You cannot just simply write the code and give it to people. So at this point, no. And actually, I didn't mention, Westinghouse is very interested. We just signed NDA, which they are looking at. We are I mentioned to Scott, modeling the AP1000 and also utilizing possibly for their microreactor as a for operation utilization. Yes. No.
So assuming with this could be used as well for fast reactors.
Yes, in principle, it's different.
Mhm.
Couple, yeah, it's different, and so the number of assembly. In principle, you can simulate any geometry, any system, because we don't, that's what another thing. I did a lot of work in multiple cross-section generation, which deterministic codes need. Here, I don't worry about any of that. I don't approximate geometry, I don't approximate energy, cross sections, so I don't have worries of those. And the whole thing is really, the physics is different, so the number of assemblies, the coupling, it changes.
When you compared to Monte Carlo, it looked like you were just comparing to brute Monte Carlo. Have you done comparisons with variance reduction?
Yeah, actually, it was variance reduction. The active value Monte Carlo, there's no variance. There's nothing. Because all the interactions are important. We do certain things, but there's not much. Shipping calculation is significant. The cadence methodology. So when I compare, I use cadence with MCP. No, if you don't do that, good luck. You get nothing. This guy, when you do these deep penetration problems, there's no way you get answer. No, I'm using the cadence, otherwise I get nothing.
Do you have any other metrics rather than the time while you are doing computation or the benchmarking? So we just did this when comparing the MCMP or other codes for Serpent, we see the time. But for example, did you also have a chance to check the memory or other metrics?
So I see where you are. The database can become large, depending on the problem and the detail you have. So the management of database can be important. At this point, we haven't got to that point because these problems are relatively small. But yes, and actually you need to develop more intelligent way of accessing your information. You can identify what problem you want to solve, then you collect that segment of your data, put it next to as opposed to trying to search through the whole database every time. Yes.
More questions? I don't see anything on the chat.
I have one last.
Yeah.
Okay.
I noticed that you have used only one core, and for MCMP or Serpent, you have different kind of core. Do you have any specific reason for that, or do you want to show that even with the one core, we do this?
Yeah, that's one of the reasons. But in principle, the part that we can somewhat speed up is this nonlinear system of equation. And I think for time dependent, in order to get cut down to 24 minutes, we are going to use. We are actually paralyzed solving the linear system. But for the others, you see, it's so fast. It doesn't make too much difference. 6 seconds, I get it 4 seconds, so it doesn't make, it's not that important.
Thank you.
Okay, let's thank our.
Thank you. Thank you. Thank you very much.
You can stay present.
Thank you very much. I appreciate everyone to be here, listening to me. I know I talk a lot, as a professor is supplying there, and you keep doing it. I try to stay on time, by the way. Normally, my friends know here, I don't. Thank you very much.